Hello everyone, welcome to the last part of this lecture. In this again we're going to do one example problem, but we are also going to understand another important concept of the related to S domain and transfer functions. We already in one of the today's example problems I already alluded to that, but this is going to become much more clear in this example problem where our we're going to realize that our output sometimes is composed of both transient responses and the steady state responses, and we're going to realize that where those responses are actually coming from the time domain. Okay, so a little bit more, right? We know that our transfer function is h of s equals y of s over x of s, right? This is how we define a transfer function, which is a ratio in the S domain, the output over input. So if you were to find the circuit's output, right, of course, this could be found by multiplying the transfer function multiplied by the input circuit's input. And both in both of these cases, both of them will be rational fractions of f as variable. Another important thing is that we have looked at these examples, and then again we are doing more examples. But another important thing is that this thing, the x of s and y of s, again these are the expression of s. Once you're gonna kind of open it up in partial fractions, you're gonna get different poles, right? And the poles are the roots of the s in the denominators. We are gonna realize that once you're going to solve this y of s and maybe convert that into the time domain, right? Once you're going to inverse Laplace transform and convert this into a time domain, we will realize that the poles of h of s is going to contribute to the transient response. And we have already seen that, but we're gonna see it much more clearly in this example problem. And the poles of this x of s is gonna contribute to a steady state response, right? So the poles of the h of s, the transfer function, contribute to transient response, and the poles of the input contribute towards the steady state components or the response. Okay, so let's do an example problems to see what I just said. Here's a function, here's a circuit. We just did that in the previous example problem as well. The circuit is the same. We already found a transfer function of this problem, so I'm not going to find the whole transfer function, but the transfer function is actually practically different, because previously we just assumed the input value to be this capital VG of S, without worrying about what that VG was, right? Now in this example problem, we are given what is the function of this VG of t, and this VG of t is 50 times t. It's a ramp, and the ramp starts at t equals to 0 because it's multiplying by a step function. Okay, so again, from previous example, right, from 13.9, our h of s, again I can show you if you maybe, right, so there you go. This was 13.9. We just have a simple VG here, and we ended up finding this thing. This is our transfer function. So I'm gonna get the same transfer function here. Write the same transfer function here. Slideshow from current. Okay. Right. So our h of s was equals to capital V naught over capital VG equals 1000 times s plus 5000 over s squared plus 6000 s plus 25 times 10 to the 6. Okay, nice. So this is good. However, the only difference is that my VG of t is 50 times t and a step function. Okay. I also know that the Laplace transform of the t is 1 over s squared, right? So the Laplace transform of Vg of t is going to come out to be 50 over s squared. Okay, so we got it. Nice. What we want to do now is, right, I got this Laplace transform. This is capital Vg of s. So I'm going to replace this capital Vg back into this equation to find V naught. So V naught of s equals 1000 s plus 5000 divided by s squared plus 6000 s plus 25 times 10 to the 6 times Vg of s, right? This Vg will go on the other side, and Vg is 50 over s square. Okay, perfect, great, right? So now you expand by partial fractions. If you were to expand this by partial fractions, right, so your capital V naught should come out to be, we also looked at this quadratic equation and found the roots of that, right? And the roots were minus 3000 plus minus j 4000. So it should come out to be K1 as plus 3000 minus j 4000. The second root should be the conjugate of it, K1 conjugate as plus 3000 plus j 4000 plus K2 over s square plus K3 over s. Okay, so we have solved many similar example problems for this partial fraction, so I'm not going to do it now, and I'm just going to write the answers of all of these K1, K1 prime, K2, and K3, right? In the past chapter, in the previous Laplace transform chapter, we did so many examples of the partial fraction expansions. So the value of the K1 is going to come out to be 5 square root 5 times 10 to the minus 4 and angle 79.70 degrees. K1 prime should be, is just a conjugate, complex conjugate, right? So your angle becomes negative. Nice. Your K2 value should be equals to 10 and K3 value equals to minus 4 times 10 to the minus 4. Okay, if you remember, in today's lecture, we just did, in one of these earlier problems, we just solved these two things. Not exactly the same, but where we have K1 and K2 prime as complex conjugates, and our denominators were complex conjugates of each other as well, right? And we use this identity a e raised to power x plus j omega t, a plus a prime ex minus j omega t. So we are going to apply that identity, and I'm going to write the final answers. And again, in these two cases, right, so for example, for this one, Laplace inverse of K2 is 10 over s square, and Laplace inverse is K3 is minus 4 10 to the minus 4 over s, should be, right? So this is practically t times ut with 10 multiplied by, right? And this is minus 4 times 10 to the minus 4 ut. And this is what we have. We can apply the same identity that we did that in the past. And I can't even tell you which example problem we did. Let me show you. Right, so I don't want to solve this whole thing again, so maybe this one? No. Yeah, this one. Yeah, where we have these two, C and D, right? So we were solving for C and D. This C and this D, where the numerators were the conjugates, and our denominators were conjugates as well, right? And we applied this identity, this whole thing here, this whole analysis here. We ended up using that to derive this equation. So you're going to do exactly the same thing over here to find the following equation that I'm going to write now. Okay. So you're gonna get the final value of over here, which is v of t. Sorry, 1 second. Okay, so your final value is gonna come out to be v naught. Should come out to be, and again this v naught is with respect to time, 10 times square root 5 times 10 to the 4, 10 to the minus 4, again a constant, e raised to power minus 3000 t, cosine of 4000 t plus 79.70 degrees, right? And plus 10 t minus 4 times 10 to the minus 4, right? And this is all multiplied by step function times volts. So here's the output value of the V naught, right? So this was the V naught in the S domain, and we Laplace inversing it into V naught of t. Again, this is what we did over here, these two functions, and these two ones is just follow exactly the same formula that I did in one of these example problems to get this component, to get this final answer, right? So this is this first value, 10 square root of 5 times 10 to the minus 4 e to the minus 3000 t, and the cosine value. This comes by applying that formula, okay? Let's do the solution. Let's do the second part now. Identify the transient component of the response. Okay. So solution B, in this V naught of t, right, which one is a transient component? I can see that this 10t minus 4 times 10 to the minus 4 is not a transient component. It's just going to continue to increase with time, right? And it's increasing even linearly. It's a linear ramp. However, this term, the first term, this entire first term, which is being multiplied by this exponent e raised to the minus 3000 t, I know at infinity is going to go down to 0, right? So my entire first part of this expression is the transient response. So transient response of V naught of t is 10 square root 5 times 10 to the minus 4 e raised to power minus 3000 t cos of 4000 t plus 79.70 degrees, right? And as t approaches to infinity, transient response approaches to 0 or decays to 0. Okay. Now let's do the solution number C. The solution number C is identify the steady state response, right? Again, this was a transient response and this is a steady state response. So the steady state response of V naught of t is 10t minus 4 times 10 to the minus 4. Right? And again, this is not decaying, right? Not decaying, and a linear ramp because of this t multiplication. So this is a steady state response. It is going to kind of continue to increase. Okay, one more important point before we do this D part, before I just kind of sketch this out. The important thing related to this concept that we talked about, the output, if your output is composed of the steady state plus a transient response, then the transient response is going to come from the transfer function, and the steady state response is going to come from the input poles. Okay, so there you go. This was your transfer function, right? And Vg was your input over here. When we converted Vg into Laplace transform, when we converted Vg into Laplace transform, right, we got 50 over s square. So we can see that your steady state response, right, this s, where is it going? Here, right? So this 50 over s square, right? And this is why when you were taking this, this generates, so 50 over s squared term, this term was generating these partial fractions, and this term is generating these two inverse Laplace transforms, right? 10 to the t and minus 4. So you can see that, right, the steady state response is generating from poles of the input, or Vg of s. And if I go back, right, here is my transfer function, which has a denominator of this quadratic equation. It was producing these two complex conjugates, right? These are the other two poles which are generating these terms, which ends up generating this term. So poles of x of s, which is your kind of input. No, sorry, this is your h of s. the transfer function. Steady state response is the poles of the input, and the transient response is the poles of the output. Okay, so after doing that, the last thing is we need to sketch V naught of t in between 0 to 1.5 millisecond, and here's a sketch. Again, on the x-axis we have in milliseconds, on the y-axis we have V naught. And this is interesting. This linear line over here is this equation. Steady state response, 10,000 T minus 0.4 millivolts, right? So we had, if you look over here, we had this thing, 10 T minus 4 times 10 to the 4 volts. So it was converted into millivolts to get 10,000 T. And it's just kind of a linear ramp, right? It kind of continues to increase. And of course, it's not going to increase like forever. But having said that, by the way, that concept is going to come more. I'm going to talk about that concept in the next lecture, maybe. And so the point that I'm trying to make over here is that this is your steady state response, 10,000 T minus 0.4 in millivolts, and it's a ramp function. Interestingly, this V naught, right, this kind of a blue curve which goes slightly away. This is your actual V naught, by the way, right? The actual V naught is slightly different than this linear ramp just because of the transient response. So this portion is due to transient response. And interestingly, this is the transient response, right? So within almost 1 millisecond, it goes away. It was a transient response. So e raised to a minus 3000 t, right, goes all the way down and make the whole transient response function almost zero. So you are only left with the steady state response, and that is why you only start to get your black line and the blue line, right? Your steady state response, which was this, and this V naught is a total response, steady state plus transient, right, becomes similar because your transient response becomes zero. That's the final comment on this topic. And in today's lecture, in kind of a 1 minute summary, in this last part of the lecture, we talked about that you can get the circuit's output by multiplying the transfer function with the input. And interestingly, the poles of the transfer function gives the transient response, and the poles of the input gives the steady state response. Yeah, and we also did a circuit problem to do it. So this is kind of an end of a lecture. And in the next lecture, we have like some other circuit problems, and we are actually going to start talking about another interesting, very important, interesting, beautiful concept of convolution. But for the next lecture, all right. Thank you so much. Have a great rest of the day. Bye.